Welcome. This is 4.5. How can you represent a function symbolically from a graph, a verbal description, or a table of values? So we're just trying to figure out how to represent functions in different ways. In class, hopefully we have the time to go ahead and just build some functions. I like to look at these like sequences and just look at the first stage. There's one block there. Second stage, we've got 4 blocks. And it's really interesting to see how your brain sees these blocks being added. We'll get into looking at that a little bit in class too. It's kind of fun to compare how people see it. In the next phase, we see 7 blocks. So we have a sequence formed here. And if you said, well, you're just adding 3 to each stage, you've already discovered your slope. Each stage you go up by 3, so you could essentially draw those points and show the increase in blocks. In a function graph, however, we always like to cross the y-axis. So in that case, we need to go backwards to our 0 stage. An easier way to do that would be to enter our number of blocks on our t-chart. So we have 1 at stage 1, 4 at 2, 7 at 3. This would be 10 at 4 because we're adding 3. And to go back to that 0 stage, all we have to do is say what plus 3 would equal 1, negative 2. Now that would be kind of tough to draw. I think some of you guys would figure out a way. But then we can finish our graph over to the y-axis at negative 2, and we can see the linear progression, straight line in other words. So those are 3 ways that we can show a function. Now on this one, we have another function shown here. Here we're starting at, it looks like 1, 2, 3, 4, 5, 6. 6 on our first term, then we drop down to 4 on our second term, 2 on our third term, 0 on our fourth term, so you can see we're losing 2 in each one. Well, that would mean that our 0th term should be up at 8 if we're going to have our first term at 6 and we follow that pattern. The 0th term is important too, as you remember from playing the function Munchkin game. The 0th term is the y-intercept in the function rule. So it goes in there. Now our m is our slope change. So like on the other one it would have been a 3 for the m. Here it will be a negative 2 for the m value. The slope is always multiplied by your independent variable. The answer to all this becomes your dependent variable. And then you could go ahead and draw or write in a pattern there. You can also do a verbal description of explaining it. Oftentimes the verbal descriptions are easier when it's a real-world problem. Here we have a diver. He's going down in the sea. He is dropping from 10 feet under the surface of the water down to 30 feet under the surface. And we find that the pressure increases from 19.1 pounds per square inch to 28 pounds per square inch. That's the force of the water on him, or it can even be the air plus the water really, because even here on land we have some pressure, pounds per square inch upon us, even above water. So if we want to know what is the pressure on him at the water's surface, we need to figure out what the pattern is here. So we can put it in a t-chart from the function Munchkin game. You know that we find the m by taking the difference here, which would be about 8.9. Just subtracted those 28 minus 19.1. I actually subtracted 20. That would be the 8. Then 0.9 would go from 20 to 19.1. And we also take this right here. So our slope is the change in the y, 8.9, over the change in the x, 20. That will be next to x equals our f of x. And we really need to find what would be our zero term. So as we go backwards here, we don't need to lower from 10 to 20, or from 10 to 30, it's 20 feet. From 0 to 10, it's only 10. So you take half of that one. You could also do it this way and take half of this one, 4.5. The other thing you can do, you can divide to get your slope. It will come out to be 0.445. Yeah, that's right. Because as we go backwards here, we want to make sure that we end up with the right amount. So 19.1 minus 4.5 would be, let's see, 19 minus 4 is 15.1, minus 0.5 would be about 14.6. Okay? So if we get the slope by dividing there, 0.445x plus our zero term, which is 14.6, we now have our function rule. Okay, we can put it on the graph. We have the 19.1 here, the 28 pounds right there, and if we connect them, because it is a continuous function, we can see that it comes in over here right about 14.1. So you have a couple different ways to check it. The zero term should be 14.6. I should have said 14.6 there. So that's kind of how we do it in word problems, explaining what it is. Now I'd like to know, what does the point F40 mean? And let's say that at F40 it is 33.5 pounds. What would that mean? If you're saying, well, it means that he's 40 feet below the surface and that he has 33.5 pounds of pressure on him, that is correct. Always remember to label your axis. So feet below surface and pounds per square inch. Okay? So that's why it's important to label these so that you don't have to stumble around trying to figure out what they actually mean. Okay, now we have a scenario that I wanted to take you through. We have a bus stop, and Mr. J drives to the bus stop and arrives 2 minutes after the bus leaves. The next bus stop is 5 miles away. Mr. J knows that the bus drives 30 miles per hour, and he's going to drive 40 miles per hour because that's the speed limit, but he's wondering, will he make it there in time to catch the bus? So we could graph this. We could say, okay, Mr. J, we need to figure out how many minutes it's going to take you to get to that bus stop. So first thing that you might say is we need to do unit analysis. This is 40 miles per hour, and we need to get rid of the hours and put it to minutes. So our hours will cancel and it'll become 40 over 60 minutes. Okay? And that's miles per minute, I should say. Miles per minute. So it's about 4/6 or 2/3 of a mile per minute. Okay? So if he starts at 0, these are the minutes. these are the miles. He would go in 1 minute, 2/3 of a mile. Let me see here, we only need 5 miles actually, so 1, 2, 3, 4, 5, that'll work. So he goes 2/3 of a mile in 1 minute. In 2 minutes, he'll go 4/3. In 3 minutes, he's going to go 2 miles. Okay. And so on and so forth. We'll just start the linear graph there. We can kind of follow it just eyeballing the linear. Okay. Now, on the bus, they're going 30 miles per hour. So when we convert that, again, the hours cancel. We get 30 over 60. So we know that they're going a half a mile a minute. Okay? But the bus has a 2-minute head start. 2 minutes would be how many miles? Because we need to start it up higher on the y-axis. If it's a half a mile in 1 minute, then in 2 minutes it would be 1 mile. So let's look at the function rule for the bus equals a half times x, number of minutes, plus 1. Because it's 2 minutes ahead, it's actually 1 mile. It's 2 minutes ahead and it's 1 mile ahead. That's why the y-axis changes on that. Now it only gains and a half. So it's going to be close whether or not they intersect. It looks like right there, about 4 minutes. Looks like it's like 6 minutes. It's about 4 miles that they intersect. Okay. So, I would ask you to actually interpret what this intersection means and make sure you remember your units on your x-axis. 6:4 would mean that in 6 minutes at mile marker number 4, Mr. J catches up to the bus. So he is going to make his bus stop if he doesn't mess around, if he just heads straight there right now. Okay? The function rule for Mr. J would have been 2/3 for his slope plus 0, because we didn't need to advance him at all on this. So that kind of shows you how we get from points to function rules. We'll see you in class.